Okay, so this is going to be a little recorded lecture on Chapter 5, continuing with Chapter 5, just to kind of keep us on track. You can hopefully watch this. If you have any questions, as always, you could always email me with questions. So where we last left off lecture, we were talking about balancing equations. So just a reminder that when we do balance equations, it is only the coefficients that change. So we never change any of the small numbers. It's always the numbers that come in front when we go to balance an equation. So here, 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 and here. And by changing those numbers in front, it allows us to make sure that we have the same number of elements on each side of the arrow. And that is the ultimate goal, is to, if you start with, say, 4 carbons, to end with 4 carbons, so that everything is the same in terms of elements on each side. Because in a chemical reaction, all that's occurring is we're just breaking apart everybody on the left-hand side, and they're recombining to make new elements on the other side. So one last thing I just want to talk about in terms of balancing is sometimes you will get these equations here that essentially will have these polyatomic ions in it. And you could definitely go through the same approach as we did before, where you make a table of your reactants and your products, and you just take every element there, and you basically figure out how many you have on each. And you could do that, but especially when you have a lot of polyatomic ions or some polyatomic ions inside an equation, sometimes it's easier just to keep them together as whole units. So what I mean is, if we look on the left-hand side here, we have 3 of the SO4 units. On the right-hand side, we have 1. So to fix that, we could kind of quickly just put a 3 in front of it. When we do that, gives us 3 of the SO4s on each side, but it also gives us 3 calciums, which tells us that's probably where we should go next. So we would go to the left-hand side for calcium, giving us 3 calciums, also giving us now 6 of the chlorines. And to fix that, we can come to the other side and put a 2 in front of it. And that 2 will give us the 6 chlorines that we need. It will also give us 2 of the irons, which we already have on that side. And that's what you'll typically see, especially when you go to balance these equations that have polyatomic ions or multiple polyatomic ions. A lot of times everything will eventually fall into place, and you'll be able to balance them a lot quicker. You could go element by element like we did, but then you would have to sort of multiply in the parentheses and out of the parentheses. So sometimes it's easier just to keep those together. And that was sort of the last thing I wanted to talk about in terms of balancing equations. So continuing on, we're going to talk about now types of reactions. And there are different ways that you could classify the same reaction, as we'll see. There's kind of 3, or kind of really 2 big classes of classifications of reactions. And the 2 really big classifications are ones that are referred to as redox reactions. I'll talk about what that means in a sec. And also, a lot of times, double displacement is also a very big topic, sort of, guys. And underneath each of these sort of big umbrellas, we will have a lot of other ways to classify the same reactions. So let's start looking at it. So the first thing we're talking about is oxidation reduction reactions. And these are, again, sometimes referred to as what I just wrote up there. These are sometimes referred to as redox reactions. And oxidation reduction reactions, a lot of times will occur a metal and a non-metal. Doesn't always have to be a metal or a non-metal, but a lot of times those will be the ones that are involved. So for example, here, if we look at this reaction here, we have sodium metal coming together with chlorine gas to form sodium chloride. And when we talk about oxidation reduction reactions, when we talk about something being oxidized, that means that it has lost electrons. While something is being reduced, that means that it gains electrons. And sometimes people remember this by Leo the Lion Goes Grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people like the oil rig. Oxidizing is losing, reducing is gaining. And these are two common ways you can remember it. A really good way sometimes to figure out what's being oxidized and what's being reduced is just a basic number line. So there's like a positive to that side, and it could get along this number transfer of electrons to the chlorine, and then it becomes positively charged. So when we look at sodium, we see it goes from 0 and it ends up at +1, which is on this side. So it is. So that's the way you can kind of simply use that little number line to figure out what's being oxidized and what's being reduced. So this is what's known as a classic redox reaction. We have our oxidation and reduction reactions, which can sometimes be written as what are referred to as half reactions. So if we look at the sodium, it is going from something with no charge to a sodium with a +1 charge, and it's given off an electron, and that is what is sometimes referred to as the oxidation half reaction. While chlorine, on the other hand, is picking up an electron, and it is then becoming 2Cl minus to balance everything out. We would need a 2 there, and a 2 there, and a 2 there, and a 2 there. And that represents really the balanced equation. And this is our reduction half reaction. And they're called half reactions because essentially if you add them back together, the electrons will cancel because they're on opposite sides of the arrow, and you would get 2 sodium plus our chlorine gas gives us 2 sodium chlorides. And that's our whole reaction from it. Now, another example would be what we have down here. This is magnesium going to oxygen plus oxygen going to magnesium oxide. Same thing here. The magnesium by itself has no charge. Oxygen, naturally, the way it comes, has no charge. Only when they come together over here, the magnesium gets a +2 charge. The oxygen gets a -1 charge. And same thing is happening here. Our magnesium is transferring electrons over to the oxygen. And again, if we look at that number line, 0 plus and minus, our magnesium again is starting at 0 and heading towards +2, which is in this direction, which means it's going through oxidation. While the oxygen is starting at 0 and heading towards half reactions, we do see the electrons always on the product side. So over here, I get to it here. We have our electrons on the product side, which is how we know it's an oxidation, as opposed to over here, our electrons will be on the reactant side. And that's how we could tell it's a reduction. Same thing over here, electrons on the product side, oxidation, and electrons over here on the reactant side. Again, a reduction reaction over here. And again, if we add these back together, we will get the overall reaction that happens over here. So these both are what can be classified as a redox reaction. They both, as we will see a little bit later on this chapter, can also be classified another way as a synthesis or combination reaction. And again, there's multiple ways to classify the same reaction. Now, another aspect of redox is an idea. We have things that are being oxidized and things that are being reduced. We also have things which are known as the oxidizing, lost my O there, agent. The oxidizing agent is the substance that is being reduced, so it's opposite of the name. And the reducing agent is the substance that is being oxidized. So it's basically opposites of each other because they cause that effect in the other thing. So the substance that goes through reduction is causing the oxidation in the other guy, while the guy that's being oxidized is causing the reduction of the other guy. So in our top example here, the sodium is going through oxidation, which means this would be our reducing agent, while the chlorine here is going through reduction, which means it is our oxidizing agent. And again, not to be confused with what is being oxidized or reduced. Again, the agents are something slightly different, basically the opposite of their names. And on the bottom here, our magnesium is being oxidized, which means it's our reducing agent. And the O2 here is being reduced, which would mean it's our oxidizing agent. So those are some aspects of a redox reaction. Now, a lot of times what we'll deal with will be metals and non-metals, but there is some definitions of oxidation reductions that basically happen when we get two non-metals together, because when we get two non-metals together, they will not transfer electrons. They basically will share electrons. So we can look at oxygen either being gained or lost. And if oxygen is gained as it goes from reactants to products, that substance is going through oxidation. And if oxygen is lost as it goes from reactants to products, then that is a definition of reduction. Hydrogen could also be a definition there if it loses hydrogen, really H2, as you go from reactants to products. Then that is also a definition of oxidation. Reduction would be if you gain, very badly written gain there, gain hydrogen. Is going through oxygen. So for most of the time, we probably won't deal too much with the oxygen hydrogen definition of redox, but we'll be looking at kind of charges, which is really known as oxidation numbers, and how those change. And you could, again, most of the time use this number line over here to help you figure it out. And here's our example of hydrogen, which is our hydrogen based. Again, if we gain more hydrogen, then it's reduction. If we lose hydrogen, it's oxidation. So carbon here lost some hydrogen. So since it lost some hydrogen, carbon here is going through, or the CH4 is going through oxidation. while our oxygen here by default would then be going through reduction. So when we talk about classifying reactions, again, redox reactions being a very kind of big umbrella under which there's a lot of sort of subcategories in terms of how we can basically identify reactions. And there's three sort of driving forces for reactions to take place. The wanting to make a precipitate, which is known as a solid, PPT stands for precipitate. Water being formed, so if you form H2O, that's another very driving force for a reaction. And the transfer of electrons, which is really the redox reactions, is where that occurs. So let's talk about one way that you can classify a reaction. So the first type of reaction is a synthesis or combination reaction. And in a synthesis or combination reaction, the general formula is right here. It's basically two things make one. So you basically put it together. So it's sometimes referred to as synthesis or combination. So here's what we got going on here. We got hydrogen gas, oxygen gas makes water. Again, two things make one is a redox reaction. Over here, sodium and chlorine come together, two things making one is your classic synthesis or combination. So again, as we talked about earlier, this is a combination to identify them. But again, this is under the big redox reactions. Now, sort of the opposite of that reaction is a decomposition reaction. And in a decomposition reaction, essentially what we're doing is the opposite of a combination or synthesis. So in a combination or synthesis reaction, we're essentially putting it together. In a decomposition reaction, the general formula is one thing makes two or more things. So one thing breaks apart into two or more things. And this is a classic decomposition reaction. It is essentially the reverse of the synthesis or combination reaction. So down here, water, if you run an electrical current over it, will break apart the hydrogen gas and oxygen gas. Again, one thing makes two things. Mercury 2 oxide, if you heat it up, will make solid mercury, liquid mercury, I'm sorry. And when we look at the oxygen with a for the oxygen. So again, if we look at it, our number line, our mercury is going from +2 +2 to 0, heading in this direction, which means it's going through reduction. And our oxygen is starting at -2 and going towards 0. And it is going through oxidation in this particular case. So this is, again, my 0 got a little scribbled on, I apologize. There we go. And again, these are also redox reactions. But again, another way that you could classify it is a decomposition reaction. So again, decomposition reactions are also oftentimes under that big umbrella of redox as well. So synthesis combination puts it together. Decomposition takes it apart. They're both could be classified as either synthesis or decomposition, but also, again, sort of broadly classified as a redox reaction as well. The next type of reaction is a single replacement reaction. And in this reaction, a couple of things. The general formula is A plus BC goes to B plus AC. So in this case, if we have A plus BC, the way you could recognize this is a couple of things. Our A over here oftentimes will be a metal that's uncombined. And up here, this is an ionic guy. So in this reaction, a metal over here has no charge to begin with. But remember, when metals get a charge, they do become positively charged. So they will come in and they will kick out the positive guy. And when they kick out the positive guy, a new ionic compound will form where the metal will gain a charge and come together with the C. And then the metal that was originally we will get a new ionic compound. Now, in order for this reaction to take place, which is a single replacement reaction, whatever is coming in needs to be more reactive than what it's replacing. So whatever is coming in needs to be more reactive than what it is replacing. And if it's not more reactive, then the reaction will not take place. So if it's not more reactive, then the reaction will not take place. So if we look up here, this is the way we can recognize zinc plus hydrochloric acid. So zinc in this state by itself, uncombined, has no charge. This is hydrochloric acid, which is essentially a positive and negative guy. So what's going to happen is the zinc's going to come in and it's going to kick out the hydrogen. Now, if you remember, when hydrogen comes out by itself in its natural form, it will come out as hydrogen gas. And you will see bubbles form when this reaction comes place. It also has no charge in this situation. The zinc chloride makes the new ionic compound. The zinc that had no charge to begin with ends up with a charge, and the chlorine also gets the same charge as over here. And if we look at this, this also is a single replacement reaction. This also will tell us that zinc is also redox reaction. Here has a plus. In this case, only the zinc and the hydrogen that's going through oxidation and reduction. And the chlorine is actually just there to balance out the charge. So it's really just the zinc and the hydrogen happening. So although, again, this is most often classified as a single displacement or a single replacement reaction, it also, as well, just like the other two that we saw there, falls under the big umbrella of redox reactions as well. Now, for example, if you had chlorine, try to do this here, chlorine plus some sodium bromide. And again, here, the chlorine has no charge. The sodium here has a +1 charge. The bromine has a -1 charge. So chlorine, which is a nonmetal, has no charge. So if this reaction takes place, the chlorine would come in and actually kick out the negative guy because it normally will make a negative charge. And when it does, we will get a new sodium in the chlorine, where the sodium has a +1 charge. Chlorine now has a negative charge. And that bromine will come out in its natural state and oxidation chloride. And kind of clean it up a little bit here. Arrows went a little crazy here today, so let's get rid of that. Just try this again here. Sorry, let's clean it up a little bit. All right. Take 2. All right, so sodium chloride. So again, the sodium here is +1. This is -1. The bromine will try to come in and kick out the chlorine, and this reaction will not take place. And we will get no reaction in this case. And that's because bromine is less reactive than chlorine, but it will not replace it. So if you know chlorine, especially when you're doing, we have fluorine, we have chlorine, afterwards as well. And again, higher in the list will replace anybody lower in the list. Anybody lower in the list will not replace anybody higher in the list. So if we go back to, say, copper, for example, solid copper plus our hydrochloric acid like we saw before. And if we were to look on this list, we would find copper lower than hydrogen on the list, which means it's less reactive, which means when it tries to come in and kick out hydrogen, it will not happen and we'll get no reaction in this case. So not all of these reactions will occur. There is, again, this sort of activity series that is sometimes used to help you decide if these reactions will take place or not. All right. So the next type of reaction we're going to talk about is actually what's known as a precipitation reaction, which of course I wrote right on the screen. That was not so good. So let's take a look at this reaction, which is a precipitation reaction, and it's actually this one up here. And basically what a precipitation reaction is, and this is again the same reaction as we see on the previous page. A precipitation reaction is basically any reaction where basically when you mix two liquids, or two solutions, I guess is a better way of saying that. When you mix two solutions, you actually make a solid. And that is what is known as a precipitation reaction. Sometimes, again, abbreviated PPT for precipitation. So a precipitation reaction is one way to classify a reaction. And that is always when we mix two solutions together and we get some type of solid that is formed. And this is also what is referred to as a double displacement reaction. So if you remember, the redox reactions was sort of a big umbrella. The double displacement reaction is also the big umbrella for which other types of reactions can fall underneath. And our double displacement one of the big ones that fall underneath that umbrella is a precipitation reaction. And again, that is just when you take two solutions, you mix them together, and a solid form. So that is definitely what is known as a precipitation reaction. Now, in a precipitation reaction, what is really happening is a double displacement reaction. And the way you can recognize that is different than others. You have AB, which is an ionic compound, and CD, which is also an ionic compound. So different than a single replacement reaction where you only have one ionic compound, the way you can identify a double displacement reaction is you actually have two ionic compounds. And basically what happens in this reaction is our two positive guys basically will switch partners. So our two cations in this case will basically switch partners. And what they will do is they will then make two new ionic compounds on the other side. And if we look up here at our precipitation reaction, that's exactly what we are seeing. So when we look up here, we have potassium chromate. Potassium is positively charged. Chromate is negatively charged. Barium is positively charged and nitrate is negatively charged. And basically what happens is the potassium over here hooked up with the negative guy over here, which is the nitrate. And that's how we get over here to potassium nitrate. And then our other positive guy, our barium, goes and connects over with our chromate and makes our second ionic compound on this side. So basically our two positive guys will switch partners. Again, looking at that top guy, the basic things that make up potassium chromate is potassium with a +1 charge because it's group 1 on the periodic table. Chromate, which is a -2 charge, which is a polyatomic ion. Barium nitrate is a +2 charge from group 2 on the periodic table. And nitrate, which is a polyatomic ion, -1 on the periodic table. So again, the potassium is coming together with our nitrate. And again, when we put these together on the other side, forget about balancing or anything like that. You always want the correct formula. So when we take +1 for potassium, -1 for nitrate, that gives us KNO3. And then people try to do both of those things at once, balance the equation and write the chemical formula on the product side. And they typically always mess up. They get the wrong formula. They get things that won't balance because they don't have the right formulas. So when you have to predict and write the products using the chemical formulas, that is the order which you want to do it. You want to get just the basic units, put them together like we did there with the potassium and the nitrate and the barium and the chromate. And then you want to get the right formulas on the product side. And then once you have all the right formulas, you then want to go back and balance it with the coefficients. So that's something people kind of mess up on a lot. They try to balance and write the formulas at the same time. Now, this reaction here is a strong acid and strong base. This is hydrochloric acid over here. And over here, this is a strong acid. And KOH, which is potassium hydroxide, is a strong base. And whenever you take a strong acid and strong base together, you pretty much get two things. You always make water, and you always make something which is an ionic compound, which is referred to as a salt, which is a fancy word for an ionic compound. And this one, when you take a strong acid and strong base together, is sometimes referred to as a acid base water. So when we look at this, this is hydrochloric acid, which is so although this is most often classified under the big umbrella of double displacement reactions as well. So these two kind of parts of the double displacement reaction take care of two of those driving forces, the formation of water, as we see in this reaction, our acid base. And we also saw the formation of a precipitate, which is what we saw in our precipitation reaction. So although they're both classified perhaps as acid-base reactions, precipitation reaction like the one we saw previously, again, both of them really a double displacement umbrella. Now, when we look at something like when we take a strong acid plus a strong base together, like what we saw over there, we get H2O. And this type of equation is sometimes what is referred to as the molecular equation. And it basically is written with everything in their correct formulas, kind of describing everything that is going on. But really in solution, anything that's aqueous, which basically means a water environment, is basically ions if it's a strong electrolyte, which all these guys are. So really in solution, what you have is H+ ions floating around. You got chloride ions floating around. You also have potassium ions floating around. You have hydroxide ions floating around. Now, when we get the water that's a pure liquid will actually stay together. It won't break apart. And we'll leave the water just like it is. Equation. And when you write the complete ionic equation, you will always, in most cases, find some ions that look exactly the same on both sides of the arrow. So if we look at this arrow and we look and we see things on both sides look exactly the same, we have Cl minus on the left-hand side. We also have Cl minus on the right-hand side. And we see K plus on the left-hand side. And we also see K plus on this side as well. These guys, which are exactly the same on both sides of the arrow, they gotta look exactly the same, should have the same amount, same charges on both sides and everything. These are what are referred to as spectator ions. And spectator ions, much like the name implies, are really not involved in the formation of what's happening in this reaction. U is only the ions that are really, in this case, coming together to make the product of this reaction, which means in this case, the overall reaction that's truly happening is the H plus from the acid is going to come together with the OH minus from the base, and we're going to make, as you guessed, water, H2O. This reaction here is what is known as the net ionic equation. And it is a reaction that basically tells you, although we mix HCl and potassium hydroxide together, what is truly happening in this reaction, the really main purpose of this reaction, is the acid is coming together with the OH minus from the base and to make water, which again, the formation of water here is one of our driving forces for a chemical reaction to take place. So again, acid-base neutralization reaction under the big umbrella double displacement. These are three types of reactions, equations that you sometimes will see for a double displacement reaction to describe what is happening. Just give me 1 second here. Try to get something to write with here. There we go. Let's see here. Give me 1 second here. There we go, I think. Technology. All right. this way here. All right. Sorry about that. All right, that should hopefully work wherever it went. There you go. All right. So as we were talking about, another sort of example of those three equations is one that we could see with a precipitation reaction, which again is a double displacement reaction. So let's say we took some sodium chloride together with some silver nitrate. And again, if we look at this, our sodium is positively charged, our chlorine is negatively charged, silver is positively charged, nitrate is negatively charged. And this is a classic double displacement reaction. Our two positive guys are going to basically switch partners. And when they do, that the sodium will hook up with the nitrate, which is sodium nitrate when they come together. And that will make something that's aqueous. Molecular equation describes what's happening here, and that's the sodium. Also, sorry, pen's still a little not so great here. Let's try this again. Fix this up a little bit. Oh, it's bad stuff out of the way. Perfect. All right. So our silver nitrate, we get it to close that. There you go. Our sodium nitrate will break apart as well. And just like our liquid, when you have anything that's a solid, it will remain together. That is essentially our precipitate. And it helps if you write the right formula in there. All right. Just like real time, I suppose. There we go. And again, this is a precipitation reaction because this is our precipitate that's being made. And this again would be our total ionic equation. And you can again look at this and look on both sides of the arrow and find ions that are the same on both sides. So in this case, if we look, we have a sodium ion over here. It looks the same as a sodium ion over here. And we have a nitrate ion on the left-hand side of the arrow, which looks the same as the nitrate ion on the right-hand side of the arrow. And again, these guys are going to be our spectator ions. So our sodium will cancel, again, because they're the same on opposite sides of the arrow. Our nitrate will cancel, kind of like an equal sign in math. If you got like X on one side and X on the other, they will cancel each other out if you move to the same side. And what that will leave you is essentially, again, in this reaction, what is truly happening, the silver from the silver nitrate will come together with the chloride from the sodium chloride. And those two guys will come together and actually make a white solid, which is known as silver chloride. And this is what is known as our net ionic equation. And again, as we saw before, this is a driving force for a chemical reaction. We have formed a solid, right? Our precipitate is formed. Just like with the acid-base reactions, we had a water being formed, our formation here of our solid, again, another driving force. And give me 1 sec, let me go find what I need to share with you here. So the question that you might have is, how do I know what will make a solid, what will not make a solid? And what will help you sort of decide that are some important rules, which are known as solubility rules. And let me just kind of find those really quick here for you. They seem to be hiding out. Too many files here. Let's see. Give me 1 second. Again, sorry about that. Let's see here. So you can use what is known as solubility rules to help you decide, is something going to be a solid? Is something not going to be a solid? And here are some of the solubility rules that you can help you make those decisions. So let me click on the right one here, I think. That should hopefully work. There we go. So these are solubility rules for things that are soluble typically in water at 25 degrees. So everybody in group 1 on the periodic table, so that's your lithium, your sodium, your potassium, if you see that in a formula, that means that it will be soluble. And if something is soluble, what that means is, I should get something to write with. That's probably what that means. Let's try that again. What that essentially means is if it is soluble, it will mix. So you won't get any type of solid that's formed. And those are the guys that get the aqueous symbol, the AQ symbol next to them in their formulas. Now, if something's insoluble, that means that when you mix them, you would expect some type of solid to form. And those guys are the guys that get the solid symbol next to them in their formulas. So these are guys that are always soluble. And when we look at it, group 1 on the periodic table, so our lithium or sodium, potassium, also anything in the formula that has NH4 plus, which is ammonium, as soon as you see that, you will know that it is soluble. Anything that contains nitrate, chlorate, or perchlorate, again, if you see those in the formula, they will be soluble. There's no exceptions for any of those guys. Now, if you have chloride, which is Cl, Br for bromide or iodide, those are soluble in everything, but there are some exceptions. So typically, if you see Cl in a formula, Br in a formula, Ri in a formula, they're going to be soluble and get that aqueous symbol. The exception would be if any one of those guys had one of these 3 guys in the formula. So if you had silver and chloride, that would be an exception. So the exception would mean that it is normally soluble. It would go from soluble to being insoluble in that case, and it would get an S. Sulfates are typically soluble, except for calcium and silver, which is slightly soluble. Barium, mercury 2, and lead sulfate, which are insoluble. So there are some exceptions here. So what we see on the screen here is things that are typically soluble. Now let's look at things that are typically insoluble, which means typically these guys on this slide are insoluble, which means they typically will get that solid symbol next to it. So hydroxides are insoluble except for alkali metals, which is group 1. So that's the same as what the other slide said. Barium and calcium hydroxide, which are slightly soluble. Slightly soluble, which is sometimes used SS, usually leans a little bit towards being insoluble, is usually what most people would consider those. But alkali metals, which is group 1 on the periodic table, is the exception. So same thing, if it normally says insoluble on this list, but it's an exception, it would go from insoluble to soluble. So if it's an exception on this list. And let's look at the equation or reaction we just did, which was sodium chloride plus silver nitrate gave us sodium nitrate. These rules to help us determine which one is soluble and which one's insoluble. So using our rules here, the first thing we do is come to this formula. And as soon as we see sodium, if you remember from the previous slide, sodium, which is group 1, is soluble in everything. There is no exception. So that's as far as you really need to go. And you could put the aqueous symbol next to it. Also, if you want to look at the second thing, which is chloride, Chlorides are soluble in everything except for silver, mercury, and lead, which in this case is not the case, right? So that still tells you it's soluble. Here, although we might not be able to find silver, we can find nitrate, and we find nitrate over here. And anything that contains nitrate is going to be soluble. Again, there are no exceptions. So that's really as far as you have to look, and you know that this guy would get the aqueous symbol next to it. Now, when we come over here to sodium, same things we saw on the other side. As soon as you see sodium, you're pretty much done. You know it's going to be aqueous. And you could also look on the last slide like we did. Nitrate is also soluble in everything. There's no exception. So you may be able to find both on the table, or you may just be able to find one on the table in terms of the ions. But one of them is usually enough to determine whether or not it'll be aqueous or soluble. And then if we look at silver, may not find silver, but we will find chloride. So if we come back, chloride again going to be soluble, except if it's hooked up with silver, mercury, or lead, which in this case, it is hooked up with silver, which means it is going to be going from soluble to insoluble in this case because it's an exception. So that's how you can use solubility rules to determine, if you mix things together, will you think that's aqueous? Will you get something that is going to be a solid? So if we look at another example here, do a little balancing, probably like a 2 there. Section. The aqueous, which means it's going to solution, no solid. Lead, although we may not be able to find lead, just like above, we were able to find nitrate, which happens. So it will be a solution and be aqueous. This side, potassium, all we need to look at. And if you didn't believe potassium, you can still look at nitrate, which will tell you this. Again, both of those things are soluble. Potassium being, again, group 1, and nitrate here, neither one has any exceptions, which means it's always going to be soluble. But now when we come to our last guy over here, we have iodide, and it's hooked together with lead. So when we come here, we see that iodide is soluble in everything except for mercury, lead, and silver, which in this case, it is hooked up with silver, which means it goes from, like we have up here, because it's an exception, it goes from being soluble to insoluble in this case. And this is actually going to be the solid that's being made here. So both of these reactions are both under the big umbrella, again, of double displacement. And they are both also precipitation reactions because they both make a solid. Same thing down here. This guy would be a precipitation reaction as they both make a solid. So solubility rules, again, will probably be provided for you. You should be familiar with how to use them. May be provided like this, or it may just be a kind of easy table to use where you basically have a positive ion in one box, a negative ion in the other box, and basically put your fingers together, and you'll either say I, which means insoluble, and should get the S, or you'll have a cation on one side, an anion on the other side, and when you put your fingers together where they meet, it will say S, which means soluble, and those guys would get the aqueous symbol. So your solubility table may look more like that, where you just simply put your fingers together between the two ions that are coming together, And you'll go to an I, which means insoluble in a solid, or an S, which means aqueous. That's the solubility rules. Let's go back to what we were talking about, I think, in our lecture here. Let's try that one here. Did not like that one. Let's try a different one. Let's try that one there. All right, that one looks like it might like. So one last type of reaction we're going to talk about, and this is what is known as a combustion reaction. And a combustion reaction, for the most part, these are the combustion reactions that most people talk about. And these are really where sometimes also referred to as hitting the wrong button. Let's try that again. They are also referred to as organic combustion reactions. And that's because it starts with something that contains carbon, hydrogen, and oxygen. So over here, like CH4, which is methane, which is the simplest organic molecule you could have. In a combustion reaction, you usually could recognize, especially an organic one, is there's O2 on the left-hand side, and the products are always CO2 and water. So the CO2 and water are your classic combustion reactions. Same thing down here, carbons and hydrogens plus O2, CO2, and water being formed is known as a combustion reaction. A variation would be combustion. On the product side, instead of CO2, you get combustion, usually starting with an organic. This is the definition of combustion, is any reaction that really involves O2. So to summarize the different types of reactions, let me find somewhere where I can maybe scribble. This looks good. We have a big umbrella of reactions, which is our redox reactions. And underneath our redox reactions, we have our synthesis, our combination. We also have our decomposition. We also have our single replacement. Reactions. Then we have sort of the big umbrella, and under we have our precipitation. And basically meet the three driving forces. Crazy pin. Sorry about that. Let's kind of clean that up a little bit. It went a little bit crazy. All right. Take 2 on that. All right. So again, we have a combustion reaction. And again, these guys, the three driving forces, which is an electron transfer, which is basically your redox reactions, the formation of water, which is your acid-base reaction, which is also your double displacement reaction. And then obviously the formation. A couple of things before I finish up here for this lecture. Let me just go find that reaction we were just writing up. Actually, this one right here. Hang on one sec. Let's go find that reaction for you. Actually, let me just do this here. Boom. So if we look at this, the one that we saw earlier, which was let's see here. It was NaCl plus silver just do it the hard way here, I guess. Sodium chloride plus silver nitrate. Again, making our sodium nitrate as we saw earlier, plus our silver chloride. So this is our precipitation reaction that we saw earlier. And again, some people may ask, is it also a redox reaction? Which is a good question. Get rid of all this chicken scratch. All right. So when we look at the charges, sodium on this side is +1, chloride is -1, the silver is +1, the nitrate is -1. When we come to this side, our sodium is still +1, our nitrate is -1, our silver is +1, and our chloride is -1. So when we look at each individual element, sodium stayed +1 and +1, Cl stayed -1 and -1, silver stayed +1 and +1, and nitrate stayed -1 and -1. There was no change in what is known as the oxidation state, or the charge, if you want to call it that for now. And so there was none when you think about our number line that we talked about with redox reactions. Nothing's moving. So sodium just stays right here, didn't change. Chloride stayed over here, it didn't change. Same thing with nitrate. Silver stayed here. Nothing went to the left, nothing went to the right. So typically speaking, when we deal with double displacement reactions, they are actually not redox reactions, which is why they're not under that umbrella of redox like we do see. So that's a very common question sometimes people have is just that, is like, is it, is it part of that redox reaction? All right, so I think for today's lecture, that is what we will basically stop at. And just give me 1 second here. So we're going to stop here. So this is sort of halfway through chapter 5. So this is really just through halfway through chapter 5. We still have a little bit more to talk about, calculations involved, reactions and stuff like that. But I did want to just kind of make this tape recording to kind of keep us on track. Again, no live lectures this week, but you could listen to this at your convenience and still kind of stay with everything. And I think I will try to record the next part of chapter 5. Again, just try to keep us on track and everything like that. All right, well, I hope you're having a good kind of little break here for the week. And again, you'll probably see the next half of this lecture happening a little bit later on in the week. Until then, I will stop for this chapter. Again, stopping here in chapter 5.